Okay, so we have a problem. The problem is we have sodium carbonate and sodium bicarbonate together in a solution. We've done a titration with hydrochloric acid. We've found a number, and then by process of elimination, that if you make one of them be X, then the other one has to be the number of moles minus that X. All right, that gets us to here. That's where we finished last week. All right, next. So we're going to solve for X. All right. Let's just explode this out. That 2 multiplies everything inside. So we multiply this by 2, and then that one by 2? No, because if we multiply them both by 2, then we're really multiplying by 1. So this is 2x over 106 plus 1.372 minus x over 84. All right, so now I have 2 fractions. I've got the common denominator problem. Remember common denominators?
Yeah, I know.
From a long time ago.
Yeah.
All right. So, first thing is, I'm going to simplify this one. If 2x over 106, then that is the same as x over half of what 106 is, 53. My numbers are rounded in my own notes. That's 106. That's 106. This becomes 53. But that would be 9/8, right? Okay. All right. And then I'm going to add to that this thing. Look at that. And what I'm going to do is I'm just going to move the x. I'm going to move the x to be here. That means that I can keep this term. I could have kept it that way before. And now I'm going to do that cross multiply thing. Okay, so 84 x's plus 53 both be over 44, 52. Which is that number by that number, right? Okay. 53 times 84 is 4,452. Okay. Now that they both have the same denominator, they can all go on one line. So the next thing is 44, 52. You know, in the textbook, none of these steps are done. It goes from there to the answer, which is fine if you're a middle school math genius, but let's work through the process. Okay, so I have 84 x's here, and I have negative 53 x's, it's an x. And I have 52 over whatever that is, of 53 times 1.37 is 68.9, all divided by that. And then at the end of this, remember, this is just the left-hand side of the equation. All of these are still equal to 0.02138. Okay. I have 84x minus 53x. That is 31x. I don't have the decimals in my own notes. I just simplified, but that is 2x over 106 is x over 53. So if you want to know what the real number is, you're going to have to tell me.
That's 31.01.
There you go. And my 68.9 stays where it is. And the 4452 stays where it is. And all of this is equal to 0.02138. Okay, getting closer to it now. So my 31.01x plus 68.9 is equal to 0.2138 multiplied by 4452. Oh, that's 31 point. So my 31.01x plus 68.9 equals, I have this as 93.49.
I got 95.18.
Is it? Okay. Maybe.
Also back there on the 68.9, I
Yeah.
got a bigger number. I got 72 for 68.9.
Is it based off of the approximation you made for the 31? Because you were using 32.
So,
It could be. 52.98 multiplied by 1.372.
I got 72.68.
Okay. Let's run through what I've got, and then we can go and we can fix it
Okay,
at our leisure. I'm assuming that the end might be off by a little bit. We'll see. We'll see. Let's do the logic. All right, and then I'm going to move that over here, which gives me 31.01x equals 93.49 minus 68.9. So your two numbers now are what, 95? You said this 0.49?
Yeah.
95.18 and 72.68, just in case. All right, so that would be our new set. I'm not saying I didn't do it wrong. 93.49 is 24.59. What I did say is it wasn't in the book. All right, so x finally is 24.59 divided by 31.01, and I did probably round up somewhere along the way. So x is 0.724. And after doing all the calculation, you lose track of what is x?
Yeah,
because we started this on Thursday. X is the grams of sodium carbonate. Sodium carbonate, sodium hydrogen carbonate. Okay. So this is a mass, it's a gram amount.
Yes.
Oh, I erased the number, that number. Just out of interest, 95.18 minus 72.68 equals what?
22.5.
Yeah, that's a different number, isn't it? 22.557. All right, let's do the 22.57 divided by 31.01 and see where this number changes.
It changes at the thousands. I got 0.72.
Okay, so that's not bad.
It's not that bad, okay.
Yeah.
It's like, there's like,
Yeah, so,
like, yeah, it's off, but it's not.
yeah, I don't know whether I rounded during my calculation
It's probably
and my
not.
numbers are different, or, yeah, probably. It's a rounding error somewhere, and it's here, which for us right now is not important, but for someone somewhere, when they're scaling this up to be thousands and thousands of kilograms, then yes, that's important, and we should do it right. Okay, so the sample contains 0.24 grams and whatever that number is.
That is
It's about the same, isn't it?
0.648.
Of sodium hydrogen carbonate. Okay. There are times when, if the two numbers are linked, you only need one of the numbers. It's a bit of a dredge sometimes to get there. Trudge. Dredge is when you scoop silt out of a waterway. Trudge is when you walk through loose medium. So not dredge, but trudge.
How do you know these definitions, Dr. Moore?
Sometimes it's a bit of a trudge, but we'll get there. Okay. All right. Let's talk about one last case where the numbers are linked. Are we good with that?
Yes.
Okay. When ions in solution are linked together, you only need to know one of them. If you know the concentration of one, it leads to the concentration of the other. Okay. Here's probably the most important. write this our way, my way, with just the H plus, and not the H2O plus H2O goes to H3O plus OH minus. Both are valid, both are equally. This one is actually probably, most people say this one is most valid. I don't like it. Just because the H3O plus ion has been spotted in crystal structures. So when you make something crystallize, it will trap water's crystallization into it. And sometimes those are protonated. And so the H3O plus has been observed trapped in the solid matrix of a crystal, which we then observe by X-ray diffraction. It's also been observed in a solvation sphere that the H3O plus is then surrounded by other waters. Okay. The old conventional thinking was that one of those, just the H plus, cannot be, and that it would be solvated, and that we would need 11 waters to surround it. Whereas now we think that the H3O plus might exist, and that it takes 4 waters with it, 3 directly hydrogen bonded to the hydrogens, and then 1 through a dipole interaction through the oxygen. But everything that they see is only in the solid state, not in the solution state. So this makes the numbers more difficult, and this makes the numbers easier. So we'll keep this one. This goes by a couple of names. This is the auto-dissociation of water. And if we were doing equilibria, real equilibria today, we're going to do equilibria of a sort, we would define that as being a liquid. So it doesn't show up in the equilibrium expression, right? Only the ions in solution show up. And if I know that, then I automatically know this, because they are linked together. The KW. KW is the concentration of products divided by the concentration of reactants, which is the H plus or the H3O plus, and the hydroxide divided by the H2O. Did I give you your purple pen back the other week?
I think so.
Because there's a purple one here. And of course, because that's a liquid, yeah, this one's no good. Because that's a liquid, it doesn't work. All right, so it turns out then that KW, that's not the case K, is just concentration of the acid multiplied by the concentration of the base. And what was that number?
1 times 10 to the negative 14.
It's the pH scale. pH scale runs from 0 to 14, because we can take the negative log of this number and it will give us 14. Okay. I'm missing something really important. This is a K. And K, equilibrium K, is the K forward divided by the K reverse, lowercase k, rate constants. And every time you tell me a rate constant, you have to tell me Who? We decided that K was too complicated to have units and we were just going to live with the number, because the number is either over there, bigger than 1, or over here, less than 1. Temperature.
Oh.
That number, because it's a K, is temperature dependent. Your book has a table on page 132. Table 6.1. And it says the value of Kw at 25 degrees Celsius is 1 times 10 to the negative 14. That's the number that we all know. But did you know that at 0 degrees Celsius, that number is 1.15 times 10 to the negative 15? And that at 50 degrees Celsius and at 100 degrees Celsius, that value is 5.3 times 10 to the 14. And 5.43 times 10 to the negative 30. Tell me about those numbers.
As you decrease the temperature, you decrease the dissociation of it, but as you increase it.
So that number is smaller
Yes.
than this number. These are getting larger. Are they large numbers?
No.
No, they're still very, very, very small numbers, but they are getting larger. So as you heat water up, more of it dissociates into its individual ions. That's called the autooxidation, or now more likely autoprotolysis. It's be called the autodissociation or autooxidation. Autooxidation is now known as the autoprotolysis of water. But there is a very small amount of H plus and a very small amount of OH minus in water when it's pure. And because they both come from the same place, they're both the same number. And the number that we have dealt with all these years is that if Kw is the H plus concentration, which is the OH minus concentration, and that is 1 times 10 to the negative 14, then whatever this is multiplied by whatever that is, they have to be the same as each other.
Yeah.
So x squared is 1.01 times 10 to the negative 14. So x, which is the concentration of H plus, is equal to the root . No?
Yeah.
Yes. Sometimes you stand so close to the board that you wonder. That's just a 1 point. Yeah. Which is why we have a pH scale, because remember, if that's H plus, then I can go pH is negative log to the base 10 of the H plus. And that gets out to be 7. Well, we have a pH scale that runs from 0 to 14 with water at 7. Okay, let's do that at a different temperature. What's the pH of water at 100 degrees Celsius? You find the value of H plus from Kw. The value of Kw is temperature dependent. So you match the temperature to the value of Kw. Kw is the concentration of H plus hydronium multiplied by the concentration of OH minus hydroxide. They both have to be the same number. For pure water, they both have to be the same number. Come up with a number. Share your number with your neighbor. If they match, then we know what we're doing. That number and that number have to be the same value. Okay. X squared is 5.43 times 10 to the negative 13. H plus is represented by X. And then pH is the negative. This number will be less than 1. So when you take the log of it, it will become a negative number. By putting the negative here, we turn the negative number into a positive number so that people will read it. People will not read negative numbers. Do to 0. You're already done. multiplied by 2.303. It's hidden in a menu somewhere. Yeah, that's the natural log. And the so what I think you might be able to do is if you divide your answer by 2.303, I think you might have the right answer. Yes, you do. But you've got to find out where the log button on your calculator is. He has a TI 89.
Oh my god.
Yeah.
89.
The natural log is 2.303 times the log, or is that the other way around? The conversion factor
Yeah.
between the two is 2.303.
I think that's right.
I think that's right. Yes, because I divided by 2.3. Yeah, it is right. Okay. We can only find the natural log button on his calculator. His actual log is somewhere in a menu. All right, so X turned out to be 7 point what?
On the,
7.37.
yes.
Okay, which gave us a pH of 6.13. Is that acidic or basic?
Acidic.
It's acidic. So when you heat water up, it becomes more acidic. What happens when you cool it down?
It becomes basic.
What was the value of H plus here? 3.39 times 10 to the negative 8. Okay, and so pH here is
7.47.
7.47, which coincidentally is the pH of blood.
What? Maybe that's why we like cold water.
Yeah.
I don't know.
So there are times, if you know one thing, you automatically know the other. How about this? And we can extend this to really, really simple things. I have a solution of HCl is 1.0 times 10 to the negative 3 moles per liter. What is the concentration of hydroxide? At 25 degrees Celsius. You want it to be 25 degrees Celsius, or you want to do an exotic number? It doesn't have to be 25. Okay, which one do you want to use? You have values of 0, 25, 50, and 100.
I want 50.
Okay, let's do that at 50. At 50 degrees Celsius, Kw equals. Did I write that one down? 50.
For water?
I did, didn't I?
Yeah, you did.
5.3. There you go. Are we on the board? Just checking that we're on the board. Kw is H plus, H minus. So, OH minus is KW over H plus, yeah. And the fact that the thing that makes this question easy, or if not easy, uncomplicated, is that HCl is a strong acid, which means it dissociates 100% in solution. That we're not setting up an equilibrium, that something dissociates and puts some H plus into solution. We're assuming that the whole value goes in. So this is 5.3 times 10 to the negative 14 over 1 times 10 to the negative 3. Oh, don't even need a calculator for that,
Oh, yeah, I was like, yeah.
because that's a 1.
Mm-hmm.
Okay, when you divide numbers that have exponents, those exponents subtract. When you multiply numbers with exponents, those numbers add. So, negative 14 minus 3. 5.3 divided by 1 is 5.3. Negative 14 minus 3 is negative 14 plus 3. So we're making the number less negative. That's a concentration. It's a unit, moles per liter. Okay, what's the pH?
Oh, wait,
we didn't have the.
Never mind. I was about to do 5 extra steps, sorry.
Yeah, so
Yeah.
you
You
have 2 ways to do this. You have that pH plus pOH equals 14, or that pH equals negative log to the base 10 of the H plus concentration, which is already in the question. So you have 2 ways. You could, now that you know the concentration of the OH minus, you could find POH and then subtract it from 14 to find the value of pH. Or you could just say,
I know it.
oh, do I need a calculator?
No,
Oh, no, you don't.
you don't.
You need to find your log button on your calculator.
I just divided by the 2.3 every time.
Mhm.
Natural.
So the pH is the negative log of 1.0 times 10 to the negative 3. 1.0 times 10 to the negative 3 is a number that is less than 1, so we'll give a negative value for a log. This will make it be positive. That is 1 divided by 1,000, which is 3 zeros. pH is 3. Okay. Let's talk a tiny bit about acids and bases before we have to talk about solutions, ions and stuff. Strong acids and strong bases are fine, but they're not nearly as chemically interesting as weak acids and bases. This is a stereotypical carboxylic acid. This one is ethanoic acid, also known as acetic acid. It H plus into solution, therefore is an acid under the Arrhenius definition. I'm gonna go ahead and call this by its old name, acetic acid, which makes this be acetate, that's its salt, and the acid itself. This is the acid. All right, now, technically, it's not. That's the acid. So when people who are thinking about solutions are thinking about acids, they're thinking about the H plus. People who are just doing general chemistry think that this is the acid. No, that's the acid. This chemically, that's the acid. But this is called acetic acid, therefore it is an acid. This is the conjugate base. Conjugate base contains one less hydrogen and it contains one more negative. It has lost an H plus. Sometimes, to avoid people confusing what really is the acid versus this acid, they will call this they'll call this hydronium, which it is, and they'll call this the free acid. I think this is going away. I don't see it being written down anymore. People still say it, but it's not going into the textbooks anymore. So acid and base, and they are paired together.
Wait, Dr. McGuire, are you saying that one is more of an acid than that one is? The hydronium is more of an acid.
Acid plus base means salt plus water. Yes. Okay. Complete ionic equation. You asked for it. In solution, there is no sodium hydroxide, there is no hydrochloric acid. There are only sodium ions, hydroxide ions, hydronium ions, chloride ions. Sodium chloride is a strong electrolyte. In solution, there is no sodium chloride. There is only sodium ions and chloride ions, and water is a liquid. That's a spectator ion, that's a spectator ion. All acid-base reactions come down to this. So what part of HCl was the acid? Is the Cl minus involved at all? No. No. Just to put it into solution. If I'd have switched this out for nitric acid, then those chlorides would be nitrates. And I wouldn't have made sodium chloride, I would have made sodium nitrate. And it still wouldn't matter because it never shows up in the net ionic equation. The net ionic equation tells you that's the acid. This is acid. More than that. We don't do too many weak bases in general chemistry. In organic, we have a bunch of them. And to be a base, you need something.
Hydroxide.
You need a lone pair of electrons. 3 definitions of being an acid. Something that increases the H plus concentration. A proton donor. or an electron pair acceptor. That is the Arrhenius definition, the Lowry-Bronsted definition, and the Lewis definition. For bases, our definitions are something that removes H plus from solution, a proton acceptor for Lowry and Bronsted, and then, under the Lewis definition, which is the best definition, an electron pair donor. And unless you have a pair of electrons to donate, you can't be a base. So all of our bases have little pairs of electrons. This base lives in equilibrium with its conjugate acid. So this is called the base. This is called its conjugate acid. A conjugate acid has one more hydrogen and one more plus than the base that it came from. This base is basic in solution because it removes H plus. It removes H plus because it strips water of a proton, an H plus, and then that hydroxide does its job. Okay? If that's the free acid, then this gets to be the free base. Those words are going away. Have you heard free base be used in the general? You should have. Before crack cocaine became crack cocaine, the word on the street was free base. No. I once upon a time, I taught chemistry 101, chemistry complete introduction, non-scientists, and I made everybody in that class stand up and do 5 or 10 minutes about anything, something at all to do with chemistry. And I only remember 2 of them. One person, a student athlete, was allergic to vitamin C.
Oh, interesting.
Yeah, and they well, I'm not sure I believe them, but they came up and they talked. And then another person came up and told us how to cook crack because their cousin did it. And,
Nice, of course.
yeah, the chemistry is very, very simple.
Yeah.
Very, very simple and profitable. But there's better ways to do that. All right. Let's have those 2 things come together. Here is your acid, and here is the base. You can put the H2O in here or leave it out. It's the same as before with just H plus and OH minus, or H2O and H2O makes H3O plus and OH minus. You get this. And that. Here's your acid, here's your base. Here is your conjugate base and your conjugate acid. And those 2 just made of salt. Those two together are the salt. But this is methylammonium acetate. Okay. That base drives the conjugate acid. This acid drives the conjugate base. This acid has an equilibrium constant for it that is specifically for its acid dissociation. It's called a Ka, and it is 1.8 times 10 to the negative 5. 1.75 times 10 to the negative 5. That base has an equilibrium constant that describes it picking up a proton and becoming the conjugate acid. It's called Kb because it's showing us it being a base. And its value of Kb is 4.47 times 10 to the negative 4. Question. If I have to deal with KBs and KAs both, I need two tables. Why don't I just write the KA for this? What's its KA? KW is KA times KB, therefore KA is KW divided by KB, which is 1.01 times 10 to the negative 14 divided by our value, 4.4 times 10 to the negative 4. KA is
2.24 times 10 to the negative 11.
Oh, 2.24. I'm gonna round that down. No, round it up. Okay. All right. Same question. What's the value of KB? 0.75 times 10 to the negative 5.
I got 5.71 times 10 to the negative 10.
We using the K that we're given at first, or the one that we found?
So these are given to you. So there's a limit. Here are our limitations. Almost everything is done at 20, in solutions, stuff is done at 25 degrees solution, degrees Celsius, and standard conditions is 1 mole per liter for those concentrations too, right? If we can't do it at standard conditions, at least we can do it at standard temperature. 1 atmosphere, 25 degrees Celsius, 298 Kelvin, okay? Almost everything's gonna be done at room temperature, which gives us this, which means we have a boundary. The pH is bounded from 0 to 14, which means that our values of Ka and Kb are somewhere up to negative 14. Unlike KSPs, KSPs will be negative 28, negative 35, little tiny things. If you were doing one of these calculations for yourself and finding out that, oh, my Ka is something 2 times 10 to the negative 20, you've done it wrong. You're outside the bounds of where you are. It is limited by that number, KW. KW is your limit, okay? Everything's gonna be inside that boundary, okay? No more to tell you about solutions and concentrations. It's all done. What comes next is the contaminant stuff, and I've held it off. I have an exam ready for you to go. I just want to put a table in it. You'll get that today. Okay?
When is it due?
I'll give you a week.
Their email?
I'll post it on Blackboard. I'll let you know when it's done. Okay. What comes next is I've made it sound worse than it is. There's a table in the book, and you pick your ions from that table, and you just add them up. And then it says these ions at these concentrations influence your solution this way. All right, I will see you Thursday morning.